Welcome back to AllAboutRx. Today we are diving into an explainer on two absolutely crucial mechanics that secretly dictate the stability and reactivity of organic molecules. We're talking about conjugation and hyperconjugation. If you've ever found yourself wondering exactly how electrons are shared across a molecule to make it tick, well, you are definitely in the right place.
Now think about this for a second. Why are some molecules just vastly more stable than others? Or why do certain chemical reactions seem to happen at very specific, totally predictable positions time and time again? It's kind of a core mystery in organic chemistry, right? But the answer actually turns out to be entirely structural.
So, here's our agenda for today's explainer. First, we'll answer what is conjugation. Second, isolated versus extended systems. Third, types of conjugation. Fourth, the power of hyperconjugation. Fifth, real-world chemical applications. And finally, number 6, a quick recall summary. Let's get into it.
Starting right off with Section 1, what is conjugation?
To really get this, let's look at the word itself. The root is Latin, and it literally means to link together. In chemistry, conjugation is specifically the linking of alternating single and multiple bonds. Basically, what's happening is that an atomic p-orbital interacts with an adjacent p-orbital right across a single sigma bond. And when these p-orbitals overlap, it creates this extra bonding, leading to electron delocalization, which you probably know as resonance energy. And that resonance energy massively stabilizes the whole molecule.
But here is the absolute golden rule you have to remember. If you rotate a carbon by just 90 degrees, you completely break that alignment. Continuous geometry is mandatory for this whole thing to work. If you do not have continuous p-orbital alignment, there can be absolutely no resonance. It's a total deal breaker.
Moving right along to Section 2, isolated versus extended systems.
We can categorize these linked systems into two main groups. First up, you have isolated systems. These involve just one pair of adjacent atoms. Think of a single carbon-to-carbon double bond. Pretty straightforward. But then you contrast that with extended systems. These are longer, continuous chains, acting almost like an electron highway, massively extending a molecule's chemical reactivity.
But remember that golden rule about uninterrupted geometry we just talked about? Take 1,4-hexadiene, for example. It is the perfect example of an interrupted chain. Because those double bonds are separated by more than one single sigma bond, a pi orbital is literally missing in the sequence. And because of that gap, the conjugation is entirely broken, making it a non-conjugated system.
All right, let's jump into Section 3, types of conjugation.
So now that we know the strict geometrical rules, let's look at the different forms these linked systems can actually take. Linear is your most common continuous chain. Then you've got cross-conjugated systems. These are branched and they have a much weaker interaction across that branch point. Cyclic linear systems are super interesting because they can be aromatic or anti-aromatic depending on their electron count. But my personal favorite is the omniconjugated system. It's this special, advanced linear case where every single branch is conjugated with every other branch. Perfectly linked, no weak cross paths, just a beautiful chemical setup. Okay, Section 4, the power of hyperconjugation.
You know, just when you think you've completely mastered the rules of pi bonds, organic chemistry throws a plot twist at you. And that twist is hyperconjugation. Think about the structure of propene. Hyperconjugation is a special case involving the delocalization of sigma electrons, like a carbon-hydrogen or carbon-carbon bond, into an adjacent p, pi, or sigma star orbital. We famously call this no-bond resonance. Why? Because the contributing structure shows literally no covalent bond between the carbon and the hydrogen, even though the hydrogen atom never actually leaves the area. It's wild.
But there is a catch. To see this no-bond resonance, you absolutely must have alpha hydrogens. It's a hard requirement. You'll see this play out beautifully in alkenes, carbocations, and free radicals. But because of this strict alpha hydrogen rule, carbanions are completely excluded from the party. You will never, ever see hyperconjugation in a carbanion.
Which brings us to Section 5, real-world chemical applications.
Theory is great and all, but let's actually apply it. This data gives us a fantastic rule of thumb. When we analyze the relative stability order for carbocations and free radicals, notice how a tertiary structure is more stable than a secondary, which is more stable than a primary, which beats a methyl. The driving force here is exactly what we just uncovered. More alpha hydrogens create more resonance structures, and more contributing structures equal vastly greater stability. It really is that straightforward.
And this invisible stabilization practically dictates macroscopic outcomes in the lab. Take toluene, for instance.
Hyperconjugation actually pushes the electron density specifically to the ortho and para positions. It's so strong that it overpowers the standard inductive effect, literally controlling where electrophilic aromatic substitution occurs.
But wait, it goes the other way too. This is called negative or reverse hyperconjugation. In molecules like alpha haloalkenes, you have these highly electronegative, greedy halogens pulling the strings. Instead of pushing electrons away, an electronegative halogen pulls the sigma electron density right toward itself, which significantly raises the molecule's overall dipole moment. Finally, let's wrap things up with Section 6, Quick Recall Summary.
We've covered a ton of ground today, so let's lock it in. Conjugation requires continuous, aligned p orbitals to create resonance energy. If that geometry is interrupted, boom, conjugation is dead. Hyperconjugation, or no-bond resonance, relies entirely on sigma electrons and alpha hydrogens. For stability, just remember the order strictly follows the number of alpha hydrogens, methyl to primary, secondary, and tertiary. And reverse hyperconjugation pulls electrons toward electronegative groups. Thanks so much for studying with me today. If you found this explainer helpful, make sure to hit that like button and subscribe to AllAboutRx for more. Before you go, ask yourself, can you spot the hidden conjugation dictating the chemical reactions all around you? See you in the next one.